So in today's video, actually I have planned something, but due to shortage of time, I would like to first complete the essential part. And today I am going to discuss that in which condition you can, if I give you the, let me first discuss the genesis of the problem. Like if I give you a if I give you a differential first order differential equation, say x dot is equal to f of x, right, where x dot is defined as dx dt. X is a vector, but this is a first order equation. Now, under which condition this differential equation will produce a guaranteed solution, and that solution will be unique in nature. So basically we are investigating the condition upon satisfying which a differential equation result, or means we can ensure that a solution will exist, that is existence of a solution and its uniqueness. So why, first of all, instead of just try to promote or means mug up the concepts, let us first understand that why it is so important here. It is important, like uh, like this is important because, say for a, if I give you a system, basically what this differential equation is, we discussed about state variable representation in our first video, and by that time means by this time you already have gained certain insight about state space representation. Now you can understand that this differential equation is representing the system dynamics. However, when we obtain a solution, that gives us that if I give you a initial value, or if you know the initial state coordinate of your system, then you can figure out that how uh, the system will reach to another state coordinate after a certain time. The essence of finding out the solution of first order differential equation is that it is, you can call the solution is the state trajectory that gives you the idea that after which, means after certain time, where your state will be. So that is why it is very important. However, unlike your linear differential equation, in case of nonlinear differential equation, we can encounter a few cases where there is no guarantee that a single solution will exist. There may be different solutions we can find. As an example, I would like to show that one simple equation that is very common to make readers, or means whoever the student understand that how multiple solution may exist for a system. So for this system you can have two solutions, like one is the common one, that if you solve it like by taking that of like then you will get some value. Typically you will get, it will result you, basically how to figure it out. Actually this way you cannot do it, you have to do it like dx by x1 by 3 is equal to dt. Now if you integrate, then this will yield, one side will be how much, like it will give you can write it like x to the power minus 1 by 3 dx dt. That is, if you solve it, will give you x to the power 2 by 3 divided by 2 by 3 t plus c 1. So if you further manipulate, you will get x of t is equal to 2 by 3t let it be this type of, so 2 by 3t c1, or this be c, here it is 3 by 2. Right, now see, so we have to figure out at x is equal to 0 what is the value we are having here. We are having like the initial condition given is x0 is equal to 0. Now that is the most problematic things, because if we try to figure out the value of this constant, then what we need to figure out, that is very important thing, like we have to put a value. So whenever you put at 0 it is 0, then it is difficult for you to find out c. Like one choice of c can be c is equal to 0, and that result in xt is equal to 0. This implies xt identically equal to 0. Another choice could be, that is common one, that take c is equal to 1, so then you will get 2t by 3 to the power 3 by 2. So obviously this one is giving you a complete different solution. Now, like instead of carrying out integration, and this one is first of all for a first order system, but if I give you a more higher order system with higher number of state variables, then things will become much more complicated. So how to deal with that, that we need to know, and herein we will formulate some, or first we will try to understand a few tools, and then we will apply those tools. So in this regard, we will introduce the concept of Lipschitz function. What is Lipschitz function? Say a function is Lipschitz So, if a function f is Lipschitz, then it will satisfy this condition. Then we can say this is a Lipschitz function. So, I can give you one example of such, like if we take x comma y, is equal to, sorry, let us take f t comma x is equal to 3x plus 2, then we can have f of t comma x1 minus f of t comma x2. So that will result in 3 of x1 minus x2. So here the Lipschitz constant is what? Lipschitz constant is L is equal to 3. Like here what we are claiming, that is very simple thing. The rate of change of your function is here our L is 3. Now another example, we can see that a function which is not Lipschitz. Let us take one example, f of t comma x square. So what we will get, it is, sorry, t comma x, that is t x square. So what you will have here, f of t comma x1 minus f of t comma x2 will be how much? T of x1 square minus t of x2 square, that will be t of x1 minus x2 into x1 plus x2. So here you can see that it is not bounded, because if we try to compare it with the standard form of Lipschitz equation, that should be f of x1 minus f of x2 less than is equal to L x1 minus x2, and L should be finite. However, this t x1 plus x2, if you compare, then this is this need to be L, but for that L is no way a finite number, because if you go on increasing the value of time, then obviously your L will be very high. So what we can say, that this f is not Lipschitz with respect to x, right? But in some other cases it can be Lipschitz, like if you take it, means try to check its whether it is Lipschitz with respect to t or not. Like here I would like to mention one thing, that if it is a function that takes 2 arguments, that you can check the Lipschitz of, means whether the function is Lipschitz or non-Lipschitz with respect to one argument itself. So the function failed to satisfy f of t x1 minus f of t x2, because x1 plus x2 can any value, even if you keep t constant, then also for x1 plus x2 can be very large. So basically your function rate of, means f of t comma x1 minus f of t of comma x2, you are finding the rate of change of the function, and the whole idea behind the Lipschitz is that the rate of change of function is less than the rate of change of your function coordinate. Rate of change of your function is less than the rate of change of its argument. That is the whole idea. So here, if the case, then you can see that this function fails to become Lipschitz with respect to this. But for finite x, you can see that this function hold good for Lipschitz with respect to t. Like if I ask you to check its function for t, then what you will get, instead of considering variation for x, you need to consider the variation for t. So you need to pass t1, t2 through that function, and you will get something x square inside that norm t1 minus t2. So for all finite value of x, you will get that the function L will become x square. So this function is Lipschitz with respect to t, but it is not Lipschitz with respect to x1, x2. Another one, we can prove that if we take a rectangle, any rectangle, how to represent a rectangle? Like you can represent it like where this close end gives you one side. Say here A, this is B, and CD is say this side. So when you take the Cartesian product of this set, you will get a collection of all point that is there in the rectangle. Now you can see that the same function which was not Lipschitz, now can we find it? Like if we take that same function here, what we will see that t norm x1 plus x2, that was the issue in the previous case. It was going out of bound when either x1 or x2 or x1 plus x2 was going out of bound. However, if we consider that function variation, like if we consider that function is bound to pick up x within this range, where it can vary only in this region, then what you can write, like this point it can pick up, like you can write this t x1 plus x2, how much it can be? It can be less than is equal to 2 max a comma b into max c comma d, right, on R. So if that is the case, then we can find out that this function becomes Lipschitz in this rectangular area. So we can say that even if it is not globally Lipschitz, we can show that for certain region it becomes Lipschitz. One more example that we use regularly, that is if we consider the time variation of your unit step function, you will see that in this region where there is a sudden jerk from 0 to 1, at that zone the function is not Lipschitz. But if you take any value of time t greater than 0, then the function is perfectly Lipschitz in this region. So I hope you get some idea about Lipschitz function. Now let us first discuss the first theorem, that is theorem of local existence and uniqueness. What does that theorem state? That let f of t comma x be piecewise linear, no, not piecewise linear, sorry, piecewise continuous in T and satisfy the Lipschitz condition for x like for all x1 comma x2 inside a ball B is equal to x belongs to Rn such that x minus x naught less than is equal to R. Then there exist some delta greater than 0 such that the state equation x dot is equal to f of t comma x with x t naught is equal to x naught as a unique solution over T0 to T0 plus delta. So let us first understand this thing very carefully, that for all let f t comma x be piecewise continuous in T. Now what is piecewise continuous? What is piecewise continuous function? Let me draw a diagram that will help you. Say you have a function piecewise continuous with respect to T. So let a function f of t comma x, but we are not considering its variation for x, we are considering its variation for only t. Then what you will get? It will behave like function. Now obviously here if you consider n-dimensional function, then this f t comma x, there will be n number of components like f1 t comma x, f2 t comma x, and at the end fn t comma x. But we are not considering that, we are considering that we consider any one of them to understand what is piecewise continuous. However, if it is an n-dimensional system, then all the n functions like all f1, f2, fn, all of them are piecewise continuous. How to draw the piecewise continuous variation? Like if f1 3, say so here you can see that these are the different regions where the functions are having continuous value. Now another function that may have a different value like even there is no necessity that the piece or the size of interval that you have picked up for first function will be the same for the second function. There is no such necessity, but only thing is that the function is such that it can be represented as a piecewise continuous function in every open subinterval. Now here, just a minute, let me check whether it's recording or not. Hello, hello, okay, it's recording. Now here you can see that we got some idea about piecewise continuous function. Now piecewise continuous in T. Obviously, if it is piecewise continuous in T, and if we can claim that piecewise continuous in X, then Laplace condition is much more stronger condition in that way. But satisfy the Laplace, not Laplace, Lipschitz condition is much more stronger condition in terms of continuity. This remain valid within the region of a ball that is defined by, this ball is defined in such a way that we have studied norm. So this is the Euclidean norm, right? X belongs to Rn. I'm trying to give you a pictorial view of this. Like you have a three-dimensional system like this. Here you are having x naught. Now what it tells that this ball is such that it is like you are having a ball around this point. So how this ball is defined? If this is our x naught, the center of this ball, then any point on that means outer surface of the ball is at a distance, means any point if you take the Euclidean distance from the center of the ball is always less than r, means always is equal to r. Means if r is the center of, means r is the radius of the ball, then we can write, say any point here we are taking x1 dash, x2 dash, x3 dash. So we can write x1 dash minus x naught 1 whole square plus x2 dash minus x naught 2 dash x naught 2 whole square, because here in a three-dimensional space, if you want to mention, say this is x1, this one is x3, and this one is x2, this side minus x2, this side you are having minus x1, this side you are having minus x3. So any point you need three coordinates. So accordingly your x0 will also have a tuple like x01, x02, x03. So that will be x03 square. So this x1 dash, x2 dash, x3 dash, they are variable, they are moving on, like you have placed a football with center at x0, and this one defines the outer surface, then this will be equal to r, and if you move inside that football, then it will become less than r, right? So in this region only we can get this condition is being satisfied by the function. Then for some delta greater than 0, we have a closed interval over time t0 to t0 plus delta, in which we will get an exact solution. Now, obvious question that may hit you, like, what is the point here? Like, we are defining the local, what we are trying to define, that localness in terms of the state variable x, not in terms of time. But while defining the range of solution, we are defining it t0 to t0 plus delta. Idea behind this is very simple. Like, you know how your every x1 is related to your x1 dot. What I am trying to say, from where all this means jargon or this theorem comes, let me explain you. You'll see here one thing that is very easy to understand, which we call the epsilon delta theorem for continuity. You must have studied it in your 12th standard. So what says in that epsilon delta definition of continuity? I would like to give you an informal description, like close points delta apart in domain maps or are mapped to close points epsilon apart. So formal definition is that a function from R to R is continuous at a point P belongs to R if given epsilon greater than 0, there exists delta greater than 0 such that P minus x less than delta implies fp minus fx less than is equal to epsilon, or sorry, less than epsilon. Well, so how this concept of continuity is applicable here? See, here if you consider our state vector components, like, let me write once again, if you consider an n-dimensional system, you are having here f1 t comma x, f of 2 t comma x, then f of n t comma x, right? Now see that we are claiming that x belongs to Rn, fine, we are also okay with that, but we are claiming that all these functions are Lipschitz with respect to x. Like if we pick up two distinct points, say xa, xb within a region defined or for all means belongs to b such that b contains all x such that norm of x minus x naught less than is equal to r. Then basically what you are saying that for all f1, f2, fn, you are picking the 2 points, or even your 2 extreme cases when the 2 points are very far away. They are the 2 points based on our statement of the theorem, the way we have presented this theorem, the points of x with respect to which we are considering all this, they are bounded to lie within a ball B of certain radius r. Now as the function is Lipschitz, so obviously with respect to x, your variation is bounded by certain constant, that is the Lipschitz constant. For f1 you can have L1, for f2 you can have L2, for fn you can have Ln. But as all these n functions are Lipschitz, you will have all the n constants, all L should be finite. Now back to the business, like here what we can say that if we take two extreme points xa and xb, they are maintaining Lipschitz relation. So obviously you can consider xa is your starting point and xb is your terminating point. So for that, in this region your function f is Lipschitz, and also you have claimed that this function is piecewise continuous with respect to t. So we can say that this xa to xb, we can claim that this is basically the band epsilon, and for that we will get a corresponding time band, like you are considering state traversal from point xa to point xb. So as the state functions, or means all the state variables, they are continuous function or piecewise continuous function of your time t, obviously they will lie inside a band of delta. Like here, if your two state points are obliged to lie inside a means confined zone, then obviously in time you need only a finite amount of time delta to traverse from one to another point. The way you have defined the state function with respect to time, it only needs a finite time to travel that finite distance in that region. So here we are getting this, the second part. Now this is all about what I have discussed. It is intuitively we are discussing. We can have a formal proof of that. If you want, then you can prove it. Now but this proof is not very important to us because we are not mathematicians. Rather, we just try to figure out, or try to not figure out, rather to gain much more insight from this problem. So if we consider that one equation which we started with, like x dot is equal to x to the power 1 by 3 with initial condition x0 is equal to 0, then what we will see that this one fx, is it Lipschitz? Let us check. Your f of t comma x is x1 to the power 1 by 3. So let us take f of t comma x1 minus f of t comma x2. So what you will get here, it will give you norm of x1 1 by 3 minus x2 1 by 3, right? Now in this juncture it is difficult for you at x is equal to 0. If you take, then what you will get here is that, or in other way you can also show it that it is not Lipschitz. Like you can carry out what is the value of f dash x. So f dash x will become 1 by 3 x of minus 2 by 3. Now as we have said, at t is equal to 0, xt is equal to 0, you can see that at x is equal to 0, this f dash x tends to infinity. So this is not Lipschitz at origin. Therefore, you cannot get a unique solution for this one, right? So what I discussed, now the same thing we can write it in a more technical manner. So let me write that. And I will try to show you the proof also for vector valued case, because most of the case our system will result in a vector valued state function. So let me write the theorem first. Let f is a function such that it is a comma b. So this one is our closed interval of time, close d to Rn be continuous for some domain D, a proper subset of Rn. Obviously that D is defined by a ball. Suppose that del f del x exists and is continuous on a comma b cross d. So actually all these are product topology, this closed interval a comma b cross d. Basically you are considering here a mapping of a function from this is if you ask me to write, then more technically we can write it is R cross Rn to Rn. Now obviously from that real line you have picked up a closed interval a comma b cross Rn, and then you are having m number of means state functions you have considered. So now see what we can have here. Now one obvious question that can comes in your mind that, sir, if we have n number of state space, then we must have n number of rate of change for them. So why it is a comma b cross d to like why not it is r cross Rn to Rn? Like we are getting n number of rate of change for n number of state variables. But my friend, we should not forget that this is a generalized representation. So unlike your state variable, it can be your output equation also. So if it is output equation, then it is very natural that you are passing your time and n state points and getting an output vector of dimension m. So if you want to represent it in form of functional mapping, then it will be from R cross Rn to Rn. So why this del f del x is need to be calculated? Like del f del x means you are having all the fm with respect to all the xn. Everyone need to be need to exist. Then we can go to write our next line that if for a convex Actually, that is why I want to cover the function analysis part, but unfortunately, due to shortage of time, I can't do that. Convex subset W, a proper subset of D, there is a constant L greater than is equal to 0 such that del f t comma x less than is equal to L on this region a comma b plus w, then we can write f of t comma t comma x minus, or you can write xa minus f of t comma xb less than is equal to L of xa minus xb for all a comma b, or all t belongs to a comma this closed interval a comma b, for all t belongs to this, and xa comma xb belongs to w. So W is a convex subset. First of all, we understand what is convex subset. Like, let us consider a two-dimensional plane here. So this kind of shape is convex subset of this plane. Why? Because you pick up any 2 points, the line that joins that point also lie in that subset. But if you pick up a star shaped one, then you will see that if this star defines your subset on a two-dimensional plane, the line that joins them is not entirely in that contains in that subset. So this one is not convex. Why this convex idea of convexity is required, that I will also explain. So but before that, let me define. Actually, please follow this proof closely, then you will get to know many things about this nonlinear system. I'm not sure whether I could complete this proof here in this lecture, because this is already almost 1 hour. Anyway, there is a few minutes left in this. So first let me explain that what it says. It is just an extension to that vector case, and do understand one thing, that in convex space, if you have 2 points x and y, then you will see that just let me write. This is the diagrammatic representation of convex set. How to write it mathematically formal way. Say xa belongs to w, xb belongs to w, and then you are having a line that is gamma s is equal to 1 minus s xa plus sxb for some value. This is in that region in the set x belongs to 0 to 1. So we can see that this gamma s will belongs to w if xa and xb belongs to w, and w is a convex set. Then we can define a line gamma s where s can take any value between 0 to 1, and gamma is the equation of line is this 1 minus s xa plus s xb, and it is like you are defining a line that join to n-dimensional point. Then that line connecting these two n-dimensional point will also belong to w, which contains the two original terminal point, right? So that one is very important. Now the remaining proof we will discuss in our next next session using Holder inequality. What Holder inequality states, like Holder inequality states, if you have non say, okay, let us take two vector z and omega, then it is less than where 1 by p plus 1 by q is equal to 1. This is Holder inequality. Before I start the next session, you may also prepare yourself by hitting Google what is Holder's inequality is, and that will ease our the understanding of this session.
Oh, sorry, it's still